Hello everyone, I hope you are doing good. Today we are going to discuss a topic which is mentioned in self-study section. Though it is not a part of syllabus, but then it is mentioned that the question can be asked from this portion. Fine. So we are going to study DC generator today. So what exactly is the meaning of DC generator? Now the name itself suggests that basically generator is a device which generates the signal. Okay, and to be precise, it is a device which converts mechanical energy into electrical energy. And how this energy conversion takes place? This energy conversion takes place according to the principle of production of dynamically induced EMF. Now what is meant by dynamically induced EMF? That we are going to see now. Now basically this is the arrangement, okay, and now we will see how exactly the signal is generated or how mechanical energy is converted into electrical energy. So here you can see that we have magnet here. So this is north pole and this is south pole. Either we can have permanent magnet or we can make use of electromagnet also. Okay, and in the between these north pole and south pole we have a coil. Okay, for our better understanding, a single coil is shown. However, we can have multiple turns in that. Fine. So this coil is there. Okay, and now what happens between north pole and south pole? There are magnetic lines of forces and the direction will be from north pole to south pole. Now since we have placed a conducting loop in between, conducting loop as in the copper, the loop which is made up of copper. So this copper loop cuts the magnetic lines of forces. Fine. Now we have already studied Faraday's law of electromagnetic induction. Now according to Faraday's law of electromagnetic induction, EMF will be produced when condition 1, either if we rotate the magnet, okay, or condition 2, if we rotate the coil. Fine. If either of these two conditions is satisfied, then there is a change in the flux linkage. Fine. Whenever there is a change in flux linkage, EMF is produced. Fine. So here what we are going to do is, in this arrangement, the magnet is not moved, but the coil is moved. So when the coil is moved, it cuts the magnetic field or magnetic flux line. And if the circuit is closed, see, this is the galvanometer. Fine. So if the circuit is closed, the current starts flowing because EMF is induced, right? And if the circuit is closed, the current starts flowing in the circuit and your galvanometer shows the reading. Okay, so what are the parts of a generator? You need to have magnetic field and you need to have a conductor or conductors if you have n number of turns which can move. Okay, if you have this arrangement, you can generate signal. Okay, now let us see how construction of DC generator looks like. Fine. So here the schematic diagram is given. You can see the 3D kind of picture here, wherein you have magnet. This is north pole and this is south pole. Fine. And this is the coil. This coil is known as armature coil. Fine. The coil which moves is known as armature coil. This armature coil is connected to commutator segment. Now what is the job of commutator? Commutator collects the current and passes this induced current to further circuit. Okay. So job of commutator is very important. Fine. And here load is connected. So commutator basically collects the generated current and passes that current through the load, and here you have brushes. Fine. Now this coil has two ends, right? So the two ends of the coils are joined to slip rings or disc, and these discs are insulated from each other. Fine. And two collecting brushes are there, and they press against the slip rings. Okay. Fine. And as I've already told you that the rotating coil is known as armature coil, and the magnets are known as field magnets. Okay. So you have now two terms, armature, and then you have field magnets. So these two things are very important. Okay. And this is the output of the generator. So this is how the signal is generated. Okay. The job of the commutator I've already explained. Now let us come to the exact working of DC generator. Fine. So here you have north pole and south pole. So you have permanent magnets. In between you have the coil placed, and there are several positions explained. Okay. You can see 1, 2, 3, 4, 5, 6, 7, 8, right? So they represent various angles. Now just imagine that the coil is exactly parallel to the field magnets. Okay. It means that it is at position 1. Fine. So I would just try to show it. Now suppose this is the magnet. So your coil will be something like this. Okay. So it allows the signal to pass through it. Signal as in the field lines. Okay. So field lines are passing from the gap. Now this whole portion is the gap, right? So it passes through this gap. Okay. So in this case the flux linkage is maximum. But what about rate of change of flux? Now there is no rate of change of flux. Fine. Because your coil is not cutting the magnetic field, rather it is passing the magnetic field. Okay. It means that in this case no EMF is induced. Understood? Now let us rotate. Now let us rotate the coil to position 2. Now when it turns slightly, flux linkage is there. Now also the magnetic field lines pass through the gap which is there in between the coil. But since we have tilted it, we have rotated it, now our conductor starts cutting the magnetic field. It means now there is rate of change of flux. Fine. So due to Faraday's law of electromagnetic induction, EMF is produced. Okay. So position 1 is here. So you do not have any voltage. Okay. Flux linkage was maximum, but rate of change of flux cut was 0. So no EMF was induced. Now you have position 2. So EMF is induced. Now let us understand that what happens when the coil is at position 3. Now position 3 is exactly perpendicular. So if you talk about the flux linkage is 0 because no flux, it does not allow the flux to pass through it, but it is cutting the magnetic flux to its maximum, right? So the rate of change of flux is maximum. Okay, so in this case you can see that maximum output is obtained. Now further it is rotated to position 4th. Now again the flux linkage increases but rate of change of flux reduces, so the EMF also reduces at point 4. Now point 5 is again 180 degree. So again what happens, flux linkage is maximum but the EMF produced is 5 because there are no flux cut in this situation. Now what happens after 180 degree? Again the same procedure continues, but since now the direction has reversed, now the voltage is produced but it is produced in the opposite direction. Okay, so likewise we get 6, 7 and 8 point. Now again the coil comes back to 0th position or 9th position and it becomes parallel. So flux linkage is maximum but rate of change of flux cutting is minimum, so we get 0 output at this position. So basically in this generator we are rotating the armature coil, right? It means we are giving mechanical energy, but what is the output? Output is the electrical energy. Correct? Okay. So this is how the signal is generated. I hope this is clear to you. Fine. Now this is the EMF equation of DC generator. So E is given by P phi N upon 60 into Z upon A. All parameters we have used till now, so we are familiar with all the parameters, right? And here N is in RPM, so it is divided by 60. Okay, if we take it in RPS, that is rotation per second, then the 60 goes away. So you can see that both the equations are almost same, but only with one difference. Here it is divided by 60 because it is in RPM, the N is in RPM, and here it is in RPS, so 60 is not there. Okay, so this is how EMF equation is represented. Now let us understand what are the various losses in DC generator. So basically there are 3 types of losses: copper loss, mechanical loss and magnetic loss. Okay, and copper loss is also represented as I square R loss, and copper loss is basically due to the material used, which is copper, because copper is a very good conductor, but then it is associated with loss also. And to your surprise, copper loss is about 30 to 40% of the full load losses, so it is the major loss. Okay, the second loss is mechanical loss. Now why mechanical loss? Mechanical loss is due to the movement. Now movement is, suppose in between you have air, so air offers friction, so losses because of air friction. Secondly, you have commutator, you have bearing and whatnot in the generator, so because of the friction in bearing and commutator, again we have a loss, and these two together are known as mechanical loss, and mechanical loss contribute to about 10 to 20% of full load losses. The last loss is magnetic loss, which is also known as iron or core loss, and the types of magnetic losses will be hysteresis loss and eddy current loss. Now we have already studied these two losses in transformer also, so we know what is hysteresis loss and what is eddy current losses. And again, magnetic losses also contribute up to 20 to 30% of the full load losses. Fine. So that's all.